Welcome. We are looking at charge flux. Charge is a conserved quantity. In the previous class, we looked at some absolute fundamentals related to charge flux, such as the charge conservation equation. We derived it. And then we looked at the very famous Maxwell's equations, the four famous Maxwell's equations that underlie all the development in all the fundamental development in electrical, electronics engineering, and so on and so forth, as well as it is necessary for biological systems. That's the reason why we are looking at this. We need some more fundamentals before we feel comfortable to attempt analysis, and therefore let us look at those fundamentals in this class. The Maxwell's equations, what we saw in the previous class, was in an integral form. Okay? And typically, the differential form is useful because then you can apply it to a small part of a system which could vary in many in directions and so on and so forth. And then that variation or those relationships, by applying these principles to a differential element, those can be integrated to get the overall picture. That would be more complete. And therefore, the Maxwell's relations in a differential form are usually useful. Therefore, let us see how to go from the integral forms to the differential forms. For that, we are going to use two important theorems in mathematics. So, to convert the integral Maxwell's equations into differential forms, we are going to use two theorems. First one is called the Gauss's theorem. Okay, recall from your initial mathematics course. You want to recall that, then stop the video here, pause the video here, recall that, and then you can restart the video. Gauss's theorem states that the surface integral over a closed surface of a certain quantity, let us say d of a vector, dot product with dA. dA is the area, differential area vector. D dot dA, the surface integral, equals the volume integral of del dot d dV. Okay. In other words, you're going from a surface integral to a volume integral. The surface integral is d dot dA, and the volume integral is del dot d of dV. Okay, so this helps in converting one type of integral to the other type of integral, surface to volume. So relationship between relevant surface and volume integrals is given by the Gauss's theorem. The second theorem is the Stokes theorem. You want to recall that also. If you want, please pause. Stokes' theorem states that the contour integral of d dot ds, remember that vector ds along the contour, d dot ds, the contour integral, equals the surface integral of del cross d dA. Okay. So this is the contour integral d dot ds equals the surface integral del cross d dA. Note that the ds is a vector along the surface, dA is a vector perpendicular to the surface. This we have seen in the previous class. So this is the relationship between the relevant contour and surface integrals. Why do we need these two things? Because our Maxwell's equations are full of these integrals, and we need to convert them. You'll see how it is done. Now, if we apply Gauss's theorem, which is the relationship between the surface and the volume integrals, to the first Maxwell's equation. What is the first Maxwell's equation, or Maxwell's first equation? Surface integral over a closed surface of epsilon naught E dot dA equals the volume integral of the charge density times dV, charge density dV, right? So this is the first equation. Now you apply the Gauss's theorem to this, the left hand side, which is the surface integral, can be converted to the equivalent volume integral. Epsilon naught E dot dA is nothing but del dot epsilon naught E dV. Okay, this is surface and this is volume. So if you replace the surface integral, note that you have volume integral on this side. So if you replace the surface integral by this volume integral, or even before the, that is what we are doing here and equating these two. So epsilon naught E dot dA equals, this is the volume integral, and from Maxwell's first equation, this is automatically equal to rho dV, a volume integral. Now dV is arbitrary. Okay, you can choose any dV, and therefore the relationship between the differential quantities must remain because the dV is arbitrary. So the volume integrals on both sides, you can not worry about them and equate the ones that are inside the integrals, the integrands. So del dot epsilon naught E equals rho, and this is the differential form of the Maxwell's first relationship. Okay, so this is the way by which you could go from an integral form to a differential form. This is for the first equation, Maxwell's first equation. Now let us consider Maxwell's second equation. Contour integral over a surface of h dot ds equals surface integral of I dash dot dA plus d dt of surface integral epsilon naught E dot dA. Okay. This is the Maxwell's second equation. You can go back and check. Now we know from Stokes' theorem that the contour integral can be converted to the corresponding surface integral using this. So d dot ds or h dot ds is del cross h dot dA. So the left hand side becomes del cross h dA over a surface, and now we have surface integral on this side and surface integrals on this side. Therefore you have this relationship, surface integral of del cross h dA equals surface integral of I dash dot dA plus d dt of surface integral epsilon naught E dot dA. So all are surface integrals, and therefore, and the surface S is fixed with time, thus the derivative can be taken inside the integral. And also, so you can take this inside because the surface is fixed with time, and the surface is arbitrary, and therefore you don't have to worry about which dA you are working with, and therefore you could equate the ones inside the integral to write del cross h equals I dash plus d dt of epsilon naught E. Now this is sum of integrals, therefore you could add them together, bring it under the same integral, and therefore I dash plus d dt of epsilon naught E. So this is the differential form of the Maxwell's second equation. What I'd like you to do is pause the video here and attempt using these theorems to convert the third and fourth Maxwell's equations into their differential forms. Can you do that? Don't worry about the time. Take as much as you want. This is the way to go about it. See whether you're able to get that. Please pause the video here and try it out. Go ahead, please. Hopefully, you could convert the other two, the third and fourth Maxwell's equations, into their differential forms. And we have a differential form of charge conservation equation that we derived in the first class on charge flux. So we'll just list them here so that you'll have it at one place for your ready reference. So this is the first equation in the differential form, Maxwell's first equation. Del dot epsilon naught E equals rho, equation 5.5-1. Del cross H equals I dash plus d dt of epsilon naught E. This is the Maxwell's second equation in differential form that we have already seen. We're just listing them down here. Equation 5.5-2. And you would have derived del cross E equals minus d dt of mu naught H by using the theorems that we just mentioned, the Gauss's theorem and the Stokes theorem. 5.5-3, and also del dot mu naught H equals 0. This is the differential form of the Maxwell's fourth equation. Okay, and of course we have our this is 5.5-4 equation number. We have our charge conservation equation in differential form that we have already derived in this form. Therefore, there is no conversion that's necessary. D rho dt plus del dot I dash equals 0. Okay. Note that I dash is the charge flux. It's not the current. The current, we use the symbol I, and we use very little of current in this course. Or rather, manipulations with current, that is. Okay. So far, we looked at the fundamentals that are necessary to analyze electrical aspects, in this case electrical aspects of a biological system. Okay. However, we have done things as has been developed by electrical engineers over the past 250, 300 years or whatever it is. Okay. Electromagnetic theory and so on and so forth. In this course, we are looking at biological systems. Okay. And most of this development has happened in vacuum. Okay, literally speaking, it is free space. All these equations are valid in free space. You recall permittivity of free space, permeability of free space, okay, epsilon naught, mu naught, because these equations have been developed in free space, and that is what the initial applications are all in electrical engineering. Whereas we need something more relevant to biological systems. Therefore, let's start looking at that next. In most biological systems, a medium is present, medium in which cells grow, and so on and so forth. So the equations that we have seen so far are valid for free space or vacuum. So recall that the electrical properties of free space, epsilon naught and mu naught, were used earlier, as I just mentioned. Or they are valid when no medium is present. When we deal with biological systems, almost always a medium is present. And when electromagnetic fields interact with the medium, or any material for that matter, the fields induce effects. And those effects need to be taken into account very clearly to have a certain base for clear analysis. Those effects are majorly of two types. One is called polarization. The second one is called magnetization in the medium. That is, they induce effects called polarization and magnetization in the medium. I was just checking whether we were at it for too long, but we can continue for some time. It may not be too tiring. Now let's look at why do polarization and magnetization occur. You may have come across these terms: polarization, separation of charges at two different ends. Okay, that's called polarization. Similar thing, magnetization. So biological media contain molecules with positive and negative charge centers that are separated by a distance. We all know this. Okay, they have molecules with positive and negative charge centers, and they are separated by a distance in biological media. In other words, they have permanent dipole moments. Charge is separated by a distance, therefore there's a dipole moment there, and these are permanent dipole moments. Water, which is found in almost all biological systems, our body is made up of, each one of our cell is made up of 70% water, and therefore our body is made up of 70% water. Water, which is found in almost all biological systems, has a permanent dipole moment, and so do biomolecules. Okay, and this is the essence of the effect. The distribution of dipoles is usually random in a biological material. However, when you apply an electric field, the dipoles would align themselves either with or against that field. Okay. When an electric field is applied, there is alignment, at least partial, of the dipoles with the field. Okay. They could align themselves either with the field or against the field, so partial alignment with the field. Such an alignment changes the electrical behavior, and such an effect is called polarization. Okay. So it is because of the nature of the biological media There are dipoles, and those dipoles could be oriented in many different directions in the absence of electrical fields or electromagnetic fields. When you apply an electromagnetic field to a biological medium, those dipoles present in the molecules align themselves either with or against the applied field, and that causes polarization. Magnetization arises due to the interaction of magnetic dipole moments with the magnetic field. And we all know that electrical and magnetic effects are coupled. Okay, that's what electromagnetism is all about. And Maxwell's equations give you the various interrelationships between those. So, the earlier written fundamental Maxwell's equations that were written for free space need to be improved when written for biological systems in a medium or under non-free space conditions. Okay. In the presence of, in a medium, in the presence of an electric field, there could be two kinds of charges. One is there could be free charges. They need not be always polarized. Okay, there could be free charges that are floating about. And of course, there are polarized charges or polarization charges. And let the charge density due to free charges be rho free charge Fc. Okay, we are going to call the charge density that arises due to free charges as rho Fc, and the charge density that arises due to polarization charges as rho Pc, polarization charges. Okay, so you have two contributions to the charge density, and we have made many developments based on that concept of charge density. So we are going to modify that fundamentally. Okay, earlier it was just rho. We didn't worry about a polarization charge. Here we are going to take into account explicitly free charges and polarization charges. So the Gauss's law can be written as, because there are two contributions to the charge density, del dot epsilon E equals, instead of rho, you have rho Fc plus rho Pc. These are charges, these are additive. So rho Fc plus rho Pc. The form of Maxwell's equations for isotropic media remain the same with the replacement of the free space permittivity epsilon naught by the medium permittivity epsilon. Okay, people have done this. I'm not going to derive that here. I'm not going to show you that the equations are pretty much the same or exactly the same, except epsilon naught, the permittivity of free space, needs to be replaced with the medium permittivity epsilon. Okay, that's the only change that is needed for the Maxwell's equations to be applicable to a medium. Isotropic medium is a uniform medium. There are no changes with space of the medium properties, or the medium in which the properties do not change with space or position. Interestingly, the permeability of most biological molecules, such as cells and tissues, can be approximated well to mu naught. Okay, so this epsilon naught permittivity takes care of the electrical modifications from an electrical viewpoint. The permeability takes care of the modifications to the from magnetic viewpoint. It so happens that mu is not very different from mu naught, or it really doesn't matter whether you use mu or mu naught. They are very close to each other, and therefore the permeability mu of most biological materials can be approximated very well to mu naught. Okay, so just by making these changes, you just need to make one change here. You don't even need to change mu, just leave it as mu naught, and your Maxwell's equations would be applicable. So this is one aspect, recognizing that we need Maxwell's equations for a biological medium, and we have modified the equations, and we found, or people have found, that there's not much of a modification that's required. You just change the permittivity of free space with the medium permittivity. That's it. The equations will be valid. Okay, we'll take it on that. The next aspect is something to do with relevant rates. Okay, this helps us significantly in reducing the complexity. As you'd have realized, those are partial differential equations. You have a time variation, space variation, and so on and so forth, right? So if we can somehow get rid of those time variations by an appropriate view, that is necessary, that is relevant for us. Okay, we cannot just take a view that's irrelevant for us. If we take a view that fits our relevance and can simplify our analysis, that is very good. And this is one such view. Okay. You recall the concept of pseudo-steady states that we did in the mass flux chapter. Recall that. This is the same concept here. Let's go through what it is. Most of the Maxwell's equations that we have seen so far are valid for electromagnetic waves. Okay, or you consider you can consider it to be in a waveform. So electromagnetic waves, and these equations are written for electromagnetic waves. We are considering the interaction of these electromagnetic waves with biological systems. When we, for our requirement, for our scope, we are looking at the interaction of these electromagnetic waves with biological systems. We are not really interested in many other things. If you look at the typical sizes of biological cells, they are of the order of microns or 10 power minus 6 meters. Whereas the wavelengths of relevance in the electromagnetic spectrum, wavelengths of relevance, that is the range of relevant wavelengths, is about 10 power 12 meters. Okay, the wavelength is, you go from 0 to a crest, then to a trough, and then back. If you look at it as an ideal sinusoid, that wavelength, the length here, is 10 power 12 meters for infra low frequency waves, and it is 10 power minus 4 meters for microwaves. Okay, this is pretty much the range that people call as a relevant range for the electromagnetic spectrum for most of our purposes. So, if you compare the size of a biological cell with the size relevant to a wave, it is something like this. Okay, this is the wavelength of the wave. This, in fact, I've kind of blown this up quite a bit. It's going to be a very small dot, but that may not be very visible. Therefore, they have kind of blown this up. This is not exactly to scale and so on. This is just to give you some idea. So the length scale of a typical cell compared with the length scale of the electromagnetic wave, just for a perception kind of a thing, not even to scale. Because this is 10 power minus 6 meters, and this is the extreme is 10 power minus 4 meters, 2 orders of magnitude higher in size. Okay, and you go to this, it is many orders of magnitude off, 18 orders of magnitude off. Okay, so the times of interaction of the wave with the biological cell are much less compared with the characteristic time of the wave. Okay, or in other words, you take the velocity 3 into 10 power 8 meter per second and divide it by the wavelength, you get the time characteristic or frequency, relevant frequency. 1 by frequency is time. So the characteristic time of the wave, and you compare the characteristic time of the wave with the times of interaction of the wave with the cell, then the times of interaction of the wave with the cell are much, much smaller compared to the characteristic time of the wave. Okay. So the lengths are very different, and therefore the times of relevance are very different. And recall that the Maxwell's relations describe this and not this. Okay. That is what is going to help us now. In other words, the rates of interactions of the waves with the biological entities, the rates of interactions, are much faster compared to the rates of interactions, rates of variation in the wave characteristics. Okay. So rates of interactions of the wave with the biological cell on one side, rates of variation of the wave characteristics on the other side, at least 2 orders of magnitude, if not 18 orders of magnitude difference is there. Okay, roughly speaking. Thus, the interactions of the waves with the biological entities can be considered to be at pseudo steady state when compared to wave processes, right? So let me read this again. The interactions of the waves with the biological entities can be considered to be at pseudo steady state when compared to the wave processes. Okay. What does this mean? This is the pseudo-steady state, right? Recall that under pseudo-steady state conditions, the variations in the rates of the much faster process can be ignored if the interest is in the slower process. Here, the Maxwell's equations describe the slower process, and therefore we can ignore the unsteady nature of the relevant interactions with the biological cell. Therefore, we can ignore the time derivatives in the relevant equations, in the Maxwell's equations. Okay. This is a big boon for us. We can completely drop off the time derivatives. Okay. That simplifies our equations considerably. We don't have partial differential equations anymore. We can directly look at ordinary differential equations if these conditions are valid. Okay. Therefore, in fact, these are actually called the electro-quasi-state and the magneto-quasi-state approximations to Maxwell's equations. These approximations are the relevant ones for use in most biological situations, and therefore we will use them. Those equations are, you have dropped out all the time derivatives. Don't worry, here it's not relevant. Del dot epsilon E equals rho, that is the first equation. Del cross H equals I dash, the other term drops out, equation 5.5-7. Del cross E equals 0, okay, the time derivatives have all gone, equation 5.5-8, and del cross mu naught H equals 0, equation 5.5-9, okay. So these are the electro-quasi-state or the magneto-quasi-state approximations to Maxwell's equations, and these are the ones that are most relevant to biological systems. An electrical potential, you all know about electrical potential right from high school, right? So let us look at that from the context of whatever we've been talking about so far in electrical description. An electrical potential is related to the electric field as E equals minus del of V. Okay, so the gradient, the gradient of V is the electric field, or the negative of the gradient of V is the electric field. Equation 5.5-10. Therefore, del dot epsilon E, okay, we are multiplying both sides by epsilon and then taking the del, pre-del. So del dot epsilon E equals del dot of minus epsilon del V. And if we substitute this 5.5 dash in 5.5-6, what is 5.5-6? It is this Gauss's law, del dot epsilon E equals rho, and we are going to substitute the electric field E in terms of the potential. We substitute that, we get del dot minus epsilon del V equals rho. So the electric field has been substituted with del V, and you have an epsilon there and so on. Therefore, del dot del is del squared. Okay. So del squared V equals minus rho by epsilon. Also note there's an error here when these two are vectors, whereas you take a dot product of the vectors, that becomes a scalar. Okay, so this is not a vector. Let me correct it right away. Yep, that's what that is. And okay, do I have any more of that? That is fine. Okay. Yeah, it's good to correct that. I'm sorry about that error. So del squared of V equals is a minus here, therefore minus rho by epsilon. Equation 5.5-11. This equation is called the Poisson equation, okay, which is very useful in the analysis of many systems. People have used this equation as such to analyze systems. Also, in the region where no charges are present, okay, let's say there are no charges present in a certain space, then you could directly write del squared V equals 0. Okay. So this equation 5.5-12 is actually called the Laplace equation. Okay. These two are useful equations in the analysis of electrical analysis of biological systems, many different systems. Certain marine organisms such as electric eels can be considered to be electric dipoles that satisfy the Laplace equation. Okay, that's one place where it can be applied. Okay, yeah, we've been at it for a while. Let's just look at one small thing and close this lecture. Constitutive equation. Okay, recall the constitutive equations that we have seen so far. Our Fick's first law, yes, right? The mass flux is directly proportional to the concentration gradient, the negative of it, and the constant of proportionality is diffusivity. Then you had the Newton's law, then you had the Fourier's law. All those were constitutive equations which are applicable over a class of substances, reasonably large class of substances, although they may not be universally applicable. We do have a constitutive equation or a few constitutive equations in electrical aspects also, and the charge flux for certain materials is directly proportional to the negative of the potential gradient. Okay. In other words, I dash is the charge flux, charge per time per unit area perpendicular to the direction of motion, equals or proportional to minus del of V, that's what this one says, and the constant of proportionality is Ke. So it can be written as Ke times the electric field, because minus del V is the electric field. Okay. So can you now guess what the constitutive equation is in this case, in the charge flux case? You've already seen this. You've already seen this many times. Okay. What is this? This is charge flux. What is this? This is conductivity. Okay. And this is potential gradient. So what does it remind you of? K is the electrical conductivity of the medium. Typical unit is Siemens per centimeter. It's a new unit, that's okay, that you'll get used to. Siemens per centimeter conductivity is given in this unit. This equation is a constitutive equation which is valid for a class of materials, and this is nothing but Ohm's law. Okay. The charge, so the current is directly proportional to the potential gradient divided by the resistance, or the 1 by the resistance is nothing but the conductance. Okay. So this is the same form. Only thing is that in the Ohm's law that you are familiar with, your current is charge per time. Here it is charge flux, so charge per time per area, and you have it of this form there. Okay. So this is nothing but a constitutive equation. Ohm's law is nothing but a constitutive equation for the charge flux situation. Okay, I think we have seen quite a few things today. In this class, we have seen the differential forms of the Maxwell's equations. We used two theorems from mathematics, the Gauss's theorem and the Stokes theorem, to go from the integral forms to the differential forms. Then we looked at the equations as relevant to biological systems, which has a medium. And then we found, or we know now, that all you need to do to the original Maxwell's equations is to replace epsilon naught with epsilon, the permittivity of free space with the permittivity of the medium. Then all those equations will be directly valid for biological systems which undergo polarization and magnetization. Okay. And then we looked at a few other things, the constitutive equation before that. We had looked at some interrelationships between the electric field, or the equations written in terms of the potential gradient. Yeah, and most importantly, before that, we saw the electroquasi-state and the magneto-quasi-state approximations, which are valid for biological systems. Those actually simplify the Maxwell's equations by taking out the time derivatives. Okay. That is similar to the pseudo steady state concept that we have already seen. Okay, that's what we did in this class. When we meet next, we'll take things forward. See you.